and what is the uh, length of the open circuited line required to replace the Z. These are the three questions we have. Okay, so first let's quickly look at the representation of the line. Okay, so this is a line, and we have a ZL present over here, right? And the length of the line is given. So this L is equal to how much? 3 lambda by 8. And they mentioned that when you look into this, the Z in equal to minus J 2.5. Right. Now, there is one, the last part of the question will be, you can have to extend this with an open circuit line, right? Such a way that this length, actually length of the open circuited line compensates this ZL. In the sense, when you make this open circuit, you can remove this ZL. So what is the length of the line? What is the length of the open circuited line is the question. Okay, so fine. So let us bring the Smith chart. All right, and let me try to solve it. Okay, now in order to answer the question, first part, uh, you see, we have to say that what is the normalized, first part of the question is find the load impedance. All right. So what first we begin with the load impedance, that is equal to minus J 2.5. Correct. That is the input impedance. Correct. So input impedance is given Z in equal to minus J 2.5. First, let us mark that on our on the Smith chart. Okay, so if you want to mark the that value, since it is negative, minus J 2.5 comes somewhere, it's a real circle. Look at the minus 2.5. So minus 2 here, this is 1.246, 1.82, this is 3. So 2.5, I am expecting this point. Okay, so this is the Z in that is given. All right, that's this point. Now, as usual, I directly draw the line connecting the center to this. So origin, I mark from the origin, draw a line passing through this. Okay, let me say this is the origin. Okay, now from this, let's read the value also, so that when we zoom in, we'll be able to see that the value at Z in, I need to measure a lambda. Okay, in terms of lambda, I should measure. So let's try to look at it. Okay, so let's try to zoom this and see. What is the value? Now the point is that I have to move. This is at the input location. This is not load, correct? This is the input impedance. So when the input impedance, I will move towards the load later, correct? I'm not going to move clockwise. I'm going to move anti-clockwise. So which scale you will read? You will read the inner scale. Is it okay? So this value is what I'm supposed to read. So that is 0.18 on this side, 19 on the other side. It's increasing value, 18, 182, 184, 186, or 186 and 188 approximately. So I'll write the value 0.188 there. Are you okay with that? So this value, what I'm writing here, whatever x I have marked, that corresponds to 0.188 lambda, maybe approximately. Okay, exact one you may see on your Smith chart. Okay, fine. So the question is, what is the load impedance? But where is the load located? Load is located, if you check the question, it's 3 lambda by 8. Are you okay? So what is 3 lambda by 2? 3 lambda by 8, that is 3 by 8. 3 by 8 is 0.375. Correct? So 0.375 I should add. So this the calculation will be like this. You need to show the calculation as well. So I'll write here. So this is location of the load, right? That is ZL. Is it okay? So ZL, so location I'm trying to calculate, that is 0.188 plus 0.375, right? We get 0. How much? 563, I guess. 0.563 lambda, correct? But you see, when I move to this point, right here, it is 0.5. In the sense, it becomes a 0. You can see that the inner circle value 0. So I need to move something extra, right? So what I do, I'll subtract 0.5 from that. Correct? So that is 0.563 lambda. On the scale, if you want to measure, you have to subtract 0.5. So 0.063 lambda is what I am supposed to move beyond the point. Okay? All right. So now let's try to zoom in. I have to go to 0.5, 0.063, correct? Okay. So 0.06 here, right? That's value. This value is 0.06, right? I have to slightly move away. So sorry. Yeah. So 0.056, 6263. I'll write the 0.063, maybe this point. Okay, this is the 0.063 lambda. Now what I'm going to do, I will mark. Okay, what I do, let me use a red color, so that's a standard notation for the point. Okay, that point I will connect to the origin. So I have to lie on the outermost line. Okay, so okay, I should use the same old color over here. This is for the reading, but the point is this, correct? So corresponding to the impedance, the point impedance, I'll mark the red color. So you see here, this is the point, correct? So we will read out that point. It is again, it is below the horizontal line. So it is always, it is lesser. Okay. Maybe this is slightly below the 0.4. So 0.4 and 0.5, it's middle, right? I can simply write this value. This is the ZL value. ZL is equal to minus J because it is below, right? J, maybe 4 point, not 4, 0.4. I'm correct. So this is not 4. Okay, it's a 0 point between 0.4 and 0.5, so slightly more than 0.4. So I'll make it as 0.4, maybe 2, because one line after, correct? Are you fine with that? Now I'm going to show how much movement we had. That is starting from this point, we were moving in this direction. So try to write it neatly. So this is how we moved, okay, in this direction. From here, all the way, we try to move like this, this, and we reached here. So that distance covered is nothing but, that is the length of the line. L is equal to 3 lambda by 8. We covered this distance to reach that point. So the value of ZL, what we get is ZL is equal to normalized, that is minus J 0.42. Okay, ohms. Again, this is a normalized, so you don't have to write a ohms over because everything. Now you see, uh, the question, the first question is over, right? What is the impedance? We could answer. So what is the impedance? First part, find the normalized load impedance. Find the distance of the voltage minimum from the load. So how do you find out? I think we have solved a similar question, right? So if you want to go for a voltage minimum, you should find out where is the Z minimum, correct? So consider the point and take that as a radius, right? So I have to consider all the way from here till here, right? This is the radius. Use that radius and make this to touch the left side. That means I'll mark the point. So this is the point, right? That is Z minimum, because when I use this as a radius, I'm going to follow this line as my path, and I'm going to reach there. So that is a Z minimum. So since this is the point, it is actually, right, the short circuit, correct? The point is correspond to Z min. So Z min equal to 0 now. It's a short circuit. Okay, just calculate what is this distance. What is the lambda you are going to measure from here to here, right? It's a direct value, 0.063. So the distance between the voltage minimum and ZL is that same distance. Okay, it's already measured, so I don't have to do anything. Simply let me write. So that is distance between ZL and the V min equal to how much? 0.063 lambda. So that answers the second part of the question. Let's move to the third part. Find the length of the open circuited line, right? Required to replace this ZL. So open circuited line means what is the impedance? Impedance is actually infinity. Okay. So along the line, where do you get infinity? Where, along that particular line, wherever we find infinity as our impedance, I have to stop. Okay, from the position of ZL, we want to move towards the new loop. Correct? Are you okay with that? So now I am actually starting from the load ZL, already marked ZL, right? I have to move certain amount of distance, that is towards the new load, right? Which direction? When I say I am going to move towards the load, which direction you are supposed to move? You are supposed to move anti-clockwise, correct? Now I need to move anti-clockwise, right? From the load, I'll mark with a maybe red color, right? From this load, I am going to move anti-clockwise, that is this direction. Are you okay? Until you reach infinity. Where is infinity? Infinity is here, right? This is the infinity. Until this you need to move until you reach that point. And now you measure how much is the distance. Correct? So this is the distance, this is the length of the line I have to use, right? So that the open circuited, the impedance becomes infinity at that. At that point, you can open circuit, right? Before that, if you open circuit, there will be a mismatch. Are you okay? Now you calculate what is the distance between these 2 points. This point is 0.063 lambda and this point is 0.25 lambda, correct? So distance of the, right, that, right, this is the calculation. Okay, so length of open circuited line to replace ZL is equal to, what is that? Calculation 0.25 lambda minus 0.063 lambda. Okay, 0.25 minus 0.063. So that is 0.187 lambda exact. Is that okay? Do you have any doubt? It's fine, right? Okay. Okay. Right. Let's go to another question. The next question is this. And air filled 50 ohm coaxial line has VSWR equal to 3.3 at 3 gigahertz. If its load gets replaced by a short circuit, then the V min on the line moves 1 centimeters towards the generator. Find ZL is a question. Look at the given data and think about an approach to solve this problem. First, let's calculate the lambda. Okay, so lambda is equal to C by F. So C is 3 into 10 to the 8 divided by 3 giga. So 3 into 10 to the 9. That is 10 to the minus 1 meters. Or this is 10 to the, if I want to make it centimeters, 10 to the minus 2 already is there. So this is 10 centimeters. Correct? All right. So we got the lambda now. And how much you are moving, right? You see here, this is the point. The VSWR, the voltage standing wave ratio, is constant for the yeah, it is value is 3.3, and that value is fixed for the complete the length of the line. For the complete line, it remains same. Okay, so okay, let's bring the this thing first. Let me bring the Smith chart, and then we'll so this is the Smith chart. I have to use the given scale because I don't have any other option. What is 3.3? I don't know. Okay, so I have to measure a radius that is equal to 3.3 VSWR. Voltage standing wave ratio should be 3.3. So I know that I have to use SWR, and I should start from the center. I should start from this point. Okay, I'll start from this point and I should measure 3.3 approximately. So this says it is 3. So this will be 3.5. So slightly lesser than that. So what I'm trying to do, I'm measuring this 3.3. So VSWR equals to 3.3 given. I'll measure, and this is my radius. Correct? Previously we did the reverse. We had a radius, we measure the VSW. Are you okay? So that is, take this as a radius. All right. So take this much radius and draw a circle on the Smith chart, keeping at the center. Right. Let me try to draw a circle. So maybe 3.3 is this much. I need double of that. So what I'll do, I'll try to draw a circle over here, and then I'll try to correct that. So if I draw approximately, maybe this looks like a circle for us. Okay, so this circle I move. So now whatever circle you see here, this is the constant VSWR circle. Is it okay? Right. Now the V min which was present earlier, where is the earlier location? This is the V min position. Correct? If you remember, where is the V min? This is the V min. Now they are saying that this V min moves towards the generator. Correct? This is going to move towards the generator. That means I have to move clockwise by how much? By the distance that is distance is not known. They say that distance is given as 1 centimeter. Correct? Yes. So let me make that calculation here. So lambda is equal to 10 centimeter. This implies the distance moved by V min equal to, so I simply use a ratio. The ratio is like this. Uh, if it is 10 centimeters, that is the lambda for, correct? Lambda is equal to 10 centimeters, right? If they say that 1 centimeter, then that is how much? I'm simply calculating that. So this is lambda into 1 divided by 10. So it is actually lambda by 10. So V min moves by lambda by 10, and they say that it is moving towards the generator, correct? So I have to move 0.1 towards the generator, that is clockwise. So what do you do? Simply draw a line here. Simply extend this V min outside. Okay, so I get a line. Measure the point here. So this value, I'm going to move the outside because I'm moving towards the generator, right? So this value is 0 lambda. So point out where is 0.1 lambda. Okay, so this is 0.01. Maybe 0.1 lambda, I am suppose 0.10, I have to move towards the generator. So towards the generator is this direction, correct? Simply move 0.1. So you see 0.1, I think I can see here, correct? So that is a point, 0.1 lambda. So this total distance will be 0.1 lambda. So simply connect them, connect that point to the center. Is it okay? Approximately, maybe this is how it's going to look. Okay, so I connected that point with the center. Now, this value itself is a 0.1 lambda. So I moved a 0.1 lambda towards this. Okay, so that means where is the new Z, right? The ZL will be this one, correct? This is a ZL, correct? So that is ZL. Can you read out how much you are getting on your graph? I'll just write that value over. You have both real and the imaginary. Okay, that in your graph, you are talking about your graph value, right? Okay, so I'll write that value. So you are getting 0.6 plus J. Okay, J 0.35. So from the graph, whatever ZL we measure is the normalized impedance. Okay, so this might vary, right? Mine is not accurate. Maybe yours is accurate. Okay, so 0.6 plus J 0.35 is the load impedance that we are measuring from this graph. Okay, that's the question which has been asked. All right, find ZL. So you see, it's actually very simple. If we use this method, it is very simple. But if we go with the normal approach, that is by using the equations and substituting the equations and solving them, this is going to be very tedious job. All right. Z naught is not given. Is given? Yeah, yeah. Okay. So 50 ohms is given, right? Yeah, please do that. Please do that. Multiply this with 50 to get the actual answer. Sorry, I didn't know that. So into 50. So this is 30 plus J 17.5 ohms. Right? Okay, perfect. So let's move further. So this is the next question. In a transmission line, VSWR is equal to 1.6 at frequency equal to 1 gigahertz. If the load gets replaced by uh, a short circuit, if the load is replaced by a short circuit, we can observe the V min moves 3 centimeters towards the load. Find ZL is a question. So this question is pretty much similar to what we have solved. Slightly different, small difference is there because we are moving towards the load. Okay, so I want you to solve by yourself, then we'll compare the answers. Okay, I'll try to write the answers we got so far. So the distance uh, covered by the V min is equal to, we are getting 0.1 lambda. Okay, so this implies the ZL value, whatever we covered, is equal to, yeah, I'll write here whatever value you got. Can you repeat? 0.06 is the answer. So since I think Z naught is not given here, right? So since it is not given, we cannot right find the actual value of the impedance. Okay, so the answer is, and ends.